So good afternoon, students. So welcome to Rapid Revision NEET series. So today we are going to discuss the thermodynamics. I hope you all are doing very well. You are solving very good number of questions, practicing very good number of questions from the PQs as well as from wherever the source we are getting. You are solving good number of questions. And so today we'll be discussing this chapter, that is thermodynamics, and in that we have also, that is KTG, kinetic theory of the gases. So together kinetic theory of the gases and thermodynamics will be solving some questions as well as we'll be discussing some major topics from this. So this chapter, if we talk about the chapter, this chapter is there as well as in class, as well as there in chemistry subject as well and physics also. But in this subject we are mostly focusing on the graphs and different processes. So we'll be discussing one by one. So let's see how this chapters appears in over 5 years. So if you see from the number of questions that is asked from the 5 years, so this blue color represents this thermodynamics and this orange color represents this kinetic theory of the gases. So even kinetic theory of the gases, we are expecting 2 questions, 1 question, 2 question, 1 question, on an average 2 questions. And in the 5 years only, from the thermodynamics, they are asking 3 questions minimum. So on an average 5 questions it is expected from the 5 years that they have been asked. So we are expecting 5 questions in coming NEET also. So this, if we talk about what we are going to discuss, that is today, molar heat capacities, degrees of freedom, that is a part of the kinetic theory of the gases we have. Then heat, work and internal energy, that is thermodynamic variables we have. Then first law of the thermodynamics. Next we have different types of processes like isothermal process, isobaric process, isochoric process and adiabatic process. Last one is cyclic process and polytropic process that we are going to cover this as well. So let's begin our journey of today's class. I hope you all are fine. You all are doing very much practice. Take the notes and pen and paper and write down what are the formulas I am going to write here. Just write it down, all of these formulas over here. So starting from this is the first fundamental table that we have already. First fundamental table, that is, so here we have the types of the gases we have: monatomic, diatomic, triatomic. This is triatomic or polyatomic we have. So in this case, this one is degrees of freedom. F is degrees of freedom. Monatomic will be having 3 degrees of freedom. Diatomic 5. This will be linear triatomic is equivalent to diatomic molecule. Next one you have the polyatomic molecule will be having 6 degrees of freedom. If we talk about the CV value, that is molar heat capacity at constant volume, this is 3 by 2R. So CV value we write here F by 2R. C value is F by 2R. And what is CP value? CP is F by 2 plus 1 into R. If you talk about the F, what is F? Degrees of the freedom. So degrees of the freedom for monatomic it is 3, for diatomic is 5, triatomic, linear triatomic, this will be 5 and this will be 6 for this. CV value F by 2R, putting the F value over here, we'll be getting this table, this particular table. You have to memorize this table or you can memorize this particular formula. From that you can get CV value as well as CP value, that is CP value is F by 2 plus 1 into R. Then here we define gamma, that is molar heat capacity at constant pressure divided by molar heat capacity at constant volume. So gamma is equals to CP by CV. And this we have gamma equals CP by CV, CP divided by CV, 5 by 2 divided by 3 by 2R. So this we are getting 5 by 3. Here we are getting 7 by 2 divided by 5 by 2, 7 by 5, again 7 by 5, and this one is 4 by 3. Second, if you talk about the CV value in terms of this, R, if you write R divided by gamma minus 1. If you solve this simplification, what is CP value? This will be gamma times of R divided by gamma minus 1. So gamma and CV value, we have this relation over here. And if I ask you gamma, what is gamma? 1 plus 2 by F. What is F here? F is nothing but degrees of freedom. Now there is one more. So here we have, so monatomic will be having 3 translation degrees of freedom. Diatomic, all the molecules will be having 3 translation degrees of freedom. But diatomic molecules and triatomic molecules and polyatomic molecules will also be having rotational degrees of freedom as well. So in this case they will be having rotational degrees of freedom as well. So what is rotational degrees of freedom? Rotational degrees of freedom in which the molecule can rotate as well. So this diatomic molecules will be having 3 translation as well as 2 rotation. Again linear triatomic molecules 3 translation plus 2 rotation. This polyatomic molecules 3 translation plus 3 rotation will be having. So here we are having total degrees of freedom for monatomic gas will be 3. So moving to next part of this, we have, so let's say solve one particular question from this, that is molar heat capacity. We know that relation, what is that? CP minus CV is equals to R. But here not they're asking this particular question. Cp is the molar heat capacity constant pressure, and this is molar heat capacity constant volume. But read the question once again. If Cp and Cv denote the specific heats, what is specific heats? Per unit mass of an ideal gas. So they're asking per unit mass. Cp value is defined for 1 mole. So if we write small c, p, we can write in terms of this Cp divided by m. And this is small cv. What is small cv? Is specific heat capacity, that is given by Cv divided by m. What is Cv? Molar heat capacity constant volume divided by m. What is m? Molar mass here. So this is defined for 1 mole of gas. So here we can write this will be Cp by m minus Cv by m is equals to this side divided by this side. This will be R by m. So this particular term will be writing this Cp minus Cv. This is a small Cp. This is small Cv is equals to R divided by m. So this particular formula, this formula is molar heat capacities, and this is formula is specific heat capacities that is defined for 1 gram of the substance. So this will be R by m. Answer will be option C over here. Next, moving next. So here the topic is various speeds of the gaseous molecules. We have the RMS speed, root mean square speed. We have the average speed. We have the most probable speed. So what is RMS speed? The RMS speed is given by under root 3 RT by m, and this in terms of this under root 3 kBt divided by small m. When to use this formula? When molar mass is given and R is ideal gas constant, T is the temperature. When to use this formula? When the Boltzmann constant is given, m is the molar mass over here. M is the molecular mass, mass of one molecule. So this is RMS value. So this is RMS speed we have. And if we talk about this one, so this one that is most probable speed. What is most probable speed? Under root 2 RT by m. So this will be given by under root 2 kBt divided by small m. Next, if we talk about this V average, the average speed given by under root 8 RT divided by pi m, and this will be under root this side 8 kBt divided by pi small m. What is difference between this one and this one? This is defined for 1 mole, that is we are defining for molar mass m, and this is defined for 1 molecular mass small m. This one is Kb defined for 1 molecule, and this is R defined for number of given 1 mole of the substance. So this is the average speed, RMS speed. The maximum value is for RMS speed. So if you see RMS speed is, you can note down this particular data, 0.92 times of V average speed. This we have this ratio, and RMS speed, this ratio will be the average speed of any molecule. The average speed of gaseous molecules is 0.92 times of VRMS, and most probable speed of any molecules will be having 0.82 times of RMS speed. So we'll be using this different, we can use different relations or different questions over here. So this all depends on temperature, this all depends on temperature, and inversely proportional to root of molar mass. So these are we have the RMS speed and most probable speed. So most probable, if we talk about this one, then let's see, coming back to this particular question, the temperature of the gas is minus 50 degrees Celsius. What is the initial temperature? So minus 50 degrees Celsius converted into Kelvin. So this will be minus 50 plus 273. We are getting this 223 Kelvin. So temperature, how much gas should be heated? To what temperature the gas should be heated? So the RMS speed is increased by 3 times. So what is initial RMS speed? V. So V should increase by, so if I write this V is given by under root 3 RT by m. So V is should be increased by how many times? V should be increased by 3 times. So initially V plus 3V. So V final should be V plus 3V. So this will be 4V. So as V is directly proportional to root of temperature, if V is becoming 4 times, so temperature should become how many times? Because it is root here we have, so temperature should become 16 times. So temperature should increase by 16 times of T. What is initial temperature? 223. So this will be 223. Initial temperature is 223. So what will be final temperature? 223 multiplied by 16. This will be 48. So we are getting this 63568. We are getting in terms of this Kelvin. What is change in temperature? What is change in temperature? So if this what we are getting, that is 3568. This is in Kelvin. If you subtract minus 273, we will be getting in terms of the temperature. So we are getting this 5. So this will be 9. This will be 3 to 95 degrees Celsius. So answer is 3 to 95 degrees Celsius. So up to this temperature, what will happen? The RMS speed of the gas molecules will increase by how many times? 4 times, because this will become 16 times, temperature will become 16 times. So moving next particular question. So here we have ideal gas law. Question is modified form of the ideal gas law. We all know what is ideal gas law. PV is equals to nRT. P is the pressure, V is the volume, N is the number of moles, R is the ideal gas constant, T is the temperature. And this particular formula we can write here, PV is equals to N kBT. Now when to use this? This is for N mole of the gas. This is for N mole of the gas. And when to use this? This is defined for N molecules of the gases. So when we write in terms of the molecules, how we are getting this? We have that relation. What is R? R is given as Kb multiplied by Na. Okay, R equals to Kb multiplied by Na. What is N here? Total number of molecules. Total number of molecules. So this Na will be total number of molecules. N is a total number of molecules. So solving this, what they're asking, a sample of given ideal gas occupies a volume V at a pressure P and absolute temperature T. Yes, we have pressure P, absolute temperature T. The mass of each molecule of the gas is small m. The following of the following gives the density of the gas. What is density? Mass is mass of divided by, sorry, what is density? So density is given by rho is equals to mass divided by volume. So mass by volume. So what is mass? How many molecules here we have? N molecules. What will be total mass? Mass of one molecule is small m. So what will be total mass? M into capital N divided by volume. This is m into capital N, that total mass divided by volume. So solve this particular case. So from here we can write what is N by V value. Then we'll substitute here. N by V value, then we'll substitute here. What is N by V value from here? N by V. So this side P by kBT. That's it. So here density rho is given by N by V, M multiplied by N by V, that is P by kBT. So this, what we are getting here? Answer we are getting, that is Pm by kT, this density. So density also in terms of this we can write here Pm by RT in terms of the for 1 molar substance, 1 mole of the substance, and in terms of the for 1 molecules, if you write this Pm by kBT. Again the same story, that is M for 1 mole, R for 1 mole, small m for 1 molecule, and this Kb for 1 molecule. So this we are getting Pm by kT. Second, we have different types of process, Charles law, Boyle's law, like that the different types of process here we have. What is the relation between the pressure P1 and P2 here? So in this case the volume, here we have the graph versus, if here the graph of volume versus temperature at 2 different pressure over here. So if we talk about this, what is actually happening? Graph is volume is proportional to temperature. So at this graph is happening at constant pressure. So different types of pressures we are having. So at this point, pressure is P1, at this pressure is P2, and we want to calculate which is having higher values, P1 or P2. Okay, fine. So we can't get it from here. So what we have to do? Just do one thing. Let's make velocity. Let's make volume as constant. So this side we are having given temperature T1, and this side we are getting temperature T2. So when the volume is constant, we are getting this. If the volume is constant, we are getting this T1, T2 is greater than T1. Using this PV is equals to nRT. We have PV is equals to nRT when the pressure into volume is equals to nRT. So what is happening here? Volume is directly proportional to temperature, but I am making the volume as constant. This volume is constant. So when the volume is constant, pressure is directly proportional to temperature. Pressure is directly proportional to temperature. So where the temperature is high, that side pressure will also be high. So in this case, I can write, so here T2, let's say corresponding here, if I talk about this, corresponding this particular point, temperature here is T1, and this side temperature here is T2, because this particular point temperature is T2, this particular point temperature is T1. So from the graph we can say T1 is greater than T2, so corresponding pressure P1 will also be greater than P2. So this we can write directly, that is P1 will be greater than P2. So from this P1 is greater than P2. Volume is when the pressure is constant. Different types of process we have. Temperature is constant, we call it as Boyle's law. In this PV is equals to constant. Then we have Charles law. When to use Charles law? When the pressure is constant. pressure is constant, Charles law. Then also we have Gay-Lussac's law. In that, volume will be constant. When the volume is constant, we use Gay-Lussac's law. Different types of process we have. This is the method that we should follow, making one variable as constant, finding the other variable like this. So moving next question over here, that is question is from the mean free path. We know what is mean free path. It is the average or successive distance travel. It is the average distance travel between successive collision of the molecules. So given a molecules will be doing Brownian motion among that. During that, what will happen? They will collide with each other. So they will make a number of collisions. Within that collisions, what is the total average distance they are traveling? That is defined as mean free path. And mean free path is given by 1 by root 2 pi n d square. Now what will this term? N is number of molecules per unit volume. So in a given room, if the volume is fixed, total number of molecules divided by volume we do, we will getting the value of the n. We call it as number density of the molecules. Okay. What is d here? D will be diameter. D will be diameter of the molecule. Okay, fine. So d will be diameter of the molecule. So here we define, that is, if we talk about this, PV is equals to n kBT, right? So what do we want? N by V. From here we want n by V. What is n by V? So this will be kBT divided by P. Putting this value, so lambda, what is lambda if we write this? 1 by root 2 pi. This is small n is nothing but n by V. So this n by V. So putting this value, this will be directly will be getting this kBT, and P will go up that side. So this will be d square. So lambda is directly proportional to pressure also. Lambda is inversely proportional to temperature. Lambda is inversely proportional to d square. What is d square? What is d? Diameter of the molecules. So here answer is option 1 by root 2 pi n d square. 1 by root 2 pi n d square, that is option Y. So moving next, that is a topic from the thermodynamics we have. So if we talk about the thermodynamics, we have different processes like heat is there, work is there, and internal energy is there. So what is heat? So suppose for example, let's say there is one beaker, and in the beaker we have gases, some amount of the gases we have, and we are hitting this by some burner. We are hitting this by a burner. We are hitting this. So let's say initially it is having some volume V. Okay. So on hitting this, what will happen? This gas, obviously on hitting the gas will absorb the heat, and gas will try to increase its volume. Initially its temperature is also T and pressure is also P. After some time, finally, so this is state 1. So any gas will have some certain coordinates, just longitude and latitude we have for determine any location. Like that, to determine the state of the gas, we should be having pressure, volume, and temperature as a coordinates here we have. So in this case, state 1 of the gas, after some time, the gases are expanding to P2, volume V2, and temperature T2. What we are giving from the outside, this is what we define heat energy. From this side, what we are getting heat energy. The first one is heat. The heat energy is given by Q, and what is Q? Nc delta T. So AC is the specific heat, and is the number of moles. Delta T is the change in temperature. So Q is equal to Nc delta T. Next we have similar. If you write in short form, this will be Nc dt. Dt is the rise in temperature. The small rise in temperature, this small change that we are giving. Dt equals to Nc dt. N is the number of moles of the gas. So this is heat that we are supplying from the outside. Second, if we talk about the work, what is work done? The work done by the gas. Mostly in physics we discuss the work done by the gas. In chemistry we are discussing work done on the gas, but here we are discussing work done by the gas, and that is given by P delta V. So P is the pressure and delta V is the change in volume. So this will be P delta V. When the pressure is constant, we'll be using this particular formula. If the pressure is not constant, we'll be using this integration of V1 to V2 P dV. If the pressure is variable, we'll be using this. If the pressure is variable, we'll be using this. And if we talk about this from mathematics part, this will give us area under. This is given by area under pressure volume graph. Area under pressure volume graph gives us work done. This gives us work done. So whenever pressure and volume axis we have some graph is there, what is the work done? Area under the PV curve. So when the pressure is, we'll be using this particular formula. Second, P delta V also we can write here NR delta T. NR delta T. We'll be discussing for each and every process as well. Third one is internal energy. What do we mean by internal energy? Internal energy is the sum of the potential energy and kinetic energy of the given gaseous molecules. So this will be sum of the potential energy plus kinetic energy. If I write potential energy plus kinetic energy of gaseous molecules is what we define internal energy. So in a given container, the molecules might have intermolecular force of attraction. They are attracting each other by intermolecular force of attraction. Because of that, they have potential energy. And second case, kinetic energy because of their molecular motion. For ideal gas, if ideal gas is there, so ideal gas, in case of ideal gas, potential energy is taken to be 0. So what is internal energy? U is equals to purely kinetic energy. Total kinetic energy we have, and this formula you can note down this NFRT by 2. What is N here? Number of moles. F is the degrees of freedom. R is the ideal gas constant. T is the temperature. NFRT by 2. Or U is equals to, also we can write here NCVT. NCVT. This is U internal energy as a function of temperature. It depends only on function of temperature if the number of moles and degrees of freedom is constant over here. Second, U is equals to NFRT by 2. Second, if we talk about the change in internal energy, delta U is equals to U final minus U initial. So this will be given by NCV delta T. Delta U is NCV delta T. This is always valid for both ideal and non-ideal gases. And delta U also we can write here NCV value R by gamma minus 1 into delta T. Right. So the delta U, these are the formulas we have for change in internal energy. Let's discuss some of the first law of thermodynamics. So first law of thermodynamics, that is one single formula, Q is equals to delta U plus W, but we have to take care of the sign convention. What is sign convention? Q is positive. Q is positive, and when to take Q as negative? Heat supplied by the system. Heat supplied on the system. Heat supplied on the system. If the system is taking heat, we have to take it as positive. When you take negative? Heat rejected by the system. System means gas. Okay, heat rejected by the gas. If the gas is rejecting heat, means we have to take it as negative. Work done, we have to take it as positive. When to take positive? Expansion. If the gas is doing expansion, volume is increasing. Volume increases, we have to take work done as positive. When to take work done as negative? If the gas is doing compression, means gas itself will not do compression, means we are compressing gas from the outside. So in that case, volume decreases. So when the volume decreases, we have to take the work done as negative. Next, delta U positive. If final potential energy is more than initial potential energy, delta U positive. If final potential is less than initial potential energy, in that case, delta U value will be negative. So delta U positive we have to take, final is more, initial is less. So that is U increases with time or temperature increases, we have to take delta U positive. Delta U negative, if U decreases with time or temperature decreases, we have to take decrease in potential energy here, that is delta U negative, and this one increase in potential, that is delta U positive. Here the gas is becoming hotter, here the gas is becoming cooler. So these are the sign convention that we have to write Q is delta U plus W along with the formula. So let's solve some of the questions from this thermodynamics part. So first one is the equilibrium state of a thermodynamic system is described by. So first one is pressure, total heat, temperature, volume, and last one is work done. So what we have to describe here, pressure, temperature, and volume are the thermodynamics states which determine the gas. So for example, right now I am at this particular place, that place will given by this particular room, and that is having some longitude as well as latitude. So that coordinates is determined by the location is determined some coordinates. Like that pressure is having certain coordinates. What is that? Like that gas is having certain coordinates. What is that? Pressure, temperature, and volume. What about heat? Heat is the physical quantity that governs the process from state A to state B. What about the work done? Again, work done is the physical quantity that governs the process from state A to state B. But all are state function: pressure, temperature, and volume. So answer will be pressure, temperature, and volume, because pressure and temperature and volume is determining the states of the gases. So if gases state is changing, means pressure is changing, temperature is changing, and volume is changing. Clear? So answer is A, C, and D. What about the work done and heat? They are governing the process from state A to state B. This one will be called as state function, and this one, total heat and work done, will be called as path function. A gaseous mixture consists of 2 moles of O2. So here we have 2 moles of O2, 2 moles of O2 plus 4 moles of argon. They're asking neglecting all the vibration modes. We don't have to consider the vibrational degrees of freedom over here. Total net energy of the system. What is U? U is equals to one formula that I gave here, that is NF RT by 2. Now here you are having, first one is oxygen, U of oxygen plus U of argon. Oxygen is diatomic molecules. What is degrees of freedom for diatomic molecule? 5. What is number of moles? 2. So 2 into F, 5 into R into temperature. So what is temperature? Temperature is T only, right? Divided by 2 plus argon, NF by 2. What is number of moles of argon? 4. 4 into what is degrees of freedom? Monatomic degrees of freedom is 3. So this will be 3 into RT divided by 2. So this, how much we are reading this? This is 12 and this one is 10. 12 plus 10, 22. 22 RT by 2. How much we are getting? 11 RT is the final answer, option C. Clear? So this is the mixture of the gases we'll be having. They'll be asking how to calculate total net energy of the system. We'll be calculating like this. One formula, single formula, NF RT by 2, where R is the degrees, R is the idealized constant, F is the degrees of freedom. Monatomic 3, diatomic 5. Moving next question over here. During an isothermal expansion, a confined ideal gas does minus 150 joule of work against the surrounding. This implies that how much heat has been removed from the gas, how much heat has been added to the gas, like that they're asking. Isothermal expansion. Okay, this question a little bit early, no problem. Isothermal means same temperature. Same temperature. Same temperature means delta T is 0. And what is delta U? NCV delta T. Delta T is 0 means delta U is also 0. If the isothermal expansions means no change in internal energy, so Q is equal to delta U plus W. Delta U is 0, then what is Q? W. Let's talk about this isothermal expansion. Confined ideal gas does minus 150 joule of work against the surrounding. So what is the Q value? Q value is minus 150 joule. As the gas is doing this much work, minus 150 joule means what is actually happening? 150 of joule is heat has been removed from the gas. 300 joule of heat has been added to the gas. 100 joule of heat has been added to the gas. So when the gas is doing work, how much work it is doing? Minus 150. So this means that minus signifies what? That gas is rejecting this much amount of heat. Yes or no? Minus signifies what? So if we are getting the minus value here, in this case, if we are getting Q value is negative, means heat is rejected by the gas. So 150 joule of heat is rejected by the gas. Right. So solving this question now. That is question from the state function and path function. Here we have a system is taken from the state A to state B via two paths ADC and ABC as shown in the figure. The internal energy at U is equal to 10 joule. So at this particular point, it is having 10 joule. They're asking so along this path. So if you talk about the path ADC, what is work along the path ADC? The amount of heat absorbed. So dQ1. What is dQ1? So dQ1 is given as 50 joule over here. And what is dW1? dW1 is 20 joule. So we can calculate here dQ1. What is dQ1? dW1, that is du plus dW1. So solving this particular case, we are getting this 50. What is 50? du plus 30. So what is du from here? Du plus 20. So this 20. So this will be du. We are getting from here, that is du is equal to 30 joule. Right. So let's talk about the second path. Where is along the path ABC? If you talk about this particular path ABC, the heat absorbed dQ2. The heat absorbed dQ2 is 36 joule. So this we can write in terms of this du plus dW2. So 36. If we talk about this du, we got it from here, right? So 30 plus dW2. What is dW2 from here? We can calculate directly. So what is dW2 we are getting? Change in internal energy will be same. You are going from initial point is A, final point is C. Initial point is A, final point is C. So there will be no change in internal energy. You go either from this path or this path because internal energy is the state function. So this from here we got, that is 6 joule. So dW2 is 6 joule. Work done along this path is 6 joule. That's it. Then here we have different types of processes. First one we have isobaric process. So isobaric process, iso means same, baric means pressure. So in this case, what happened? Pressure of the gas is constant. This process in which pressure of the gas is constant. If you talk about the states of the gas, P, volume V1, temperature T1, volume will change, pressure will not change, P V2, temperature T2. So what will be, if you talk about this, so what is the change in internal energy in this case? Delta U, again delta U will be same, that is NCV delta T, that is not going to change for different process, NCV delta T, and that is given by N CV delta T, or we can also write here NR gamma minus 1 into delta T. And if we solve this particular case, also we will getting this delta U is equals to P2 V2 minus P1 V1 divided by gamma minus. Solving this, NR delta T will be getting this. So what is work done? Work done is P delta V, just because pressure is constant, we can use direct formula this. And second is Q value, if they're asking Q value, first is delta U plus W. You calculate delta U, calculate W. From here you can calculate, or directly you can write Q is equals to N Cp delta T. So N Cp delta T. So this will be heat that is supplied at constant pressure. Next we have isobaric process. Next we have isochoric process. Isochoric. Iso means same, core means volume. So in this case, same volume process, that is volume is constant. So when the volume is constant, if we talk about when the pressure is constant, we call it as isobaric process. They will mention in the question sometime open vessel is there. They will mention like this. Then volume is constant. If the volume is constant, we will be writing this. Volume is constant, closed and fixed vessel. When the vessel is fixed and closed, so this will be defined as volume is constant, closed and fixed vessel. So what is pressure? P1 volume V, temperature is T1, to pressure P2 volume is V, temperature is T2. So this volume is not changing in this case. So what is delta U? Again delta U will be same. What is that? NCV delta T. Delta will be same, NCV delta T, or we can write here NR divided by gamma minus 1 into delta T. Second, delta U also we can write here P into V2 minus V1 divided by gamma minus 1. Volume is not changing, so here we can write V P2 V2 minus P1 means V into P2 minus P1 divided by gamma minus 1. Second, that is work done will be 0. Why it will be 0? P delta V, change in volume is 0, so that's why work done will also be 0. Third one, Q is equals to delta U plus W. As work done is 0, so Q is equals to delta U. That we have to focus over here. Whatever the heat we are supplying, that is equals to change in internal energy. In case of which process? Isochoric process. Next we have isothermal process. So what is isothermal process? We know that iso means same, thermal means temperature. So in this case, a process in which temperature is constant, we call it as isothermal process. So this side P1 V1 is equals to P2 V2 is equals to PV is equals to constant. So this particular formula, that is P equals to nRT, temperature is constant for given mole of the gas, P equals to constant. So what is delta NCV delta T we have, right? But change in temperature is 0, so this delta U value will be 0. What is work done? We have the formula, direct formula. I am not writing how we are getting this, just writing this 2.30 nRT log V2 by V1. And what is Q value? Q is again Q is delta U plus W. Delta U is 0, so what is Q? Q is equals to W. So whatever the heat we are giving in isothermal process, that heat will be equal to total work done by the gas. Okay, so this is isothermal process. Last part, that is adiabatic process. If you talk about the adiabatic process, so adiabatic process is the process in which we have this particular relation, that is PV की power gamma equals to constant. So when the PV की power gamma equals to constant, that is adiabatic process. Second, TV की power gamma minus 1 equals to constant. Second, T1 minus gamma T की power gamma is equals to constant. That is the adiabatic process we have. So state 1, in this case all will be changed, pressure, volume, temperature will change. Pressure P1 V1, temperature T1 will change to pressure P2 V2 and temperature T2. What is delta U? Simple formula NCV delta T. This is not going to change. Okay, so adiabatic process, the process in which no heat exchange to the surrounding. It is insulating wall, insulating vessel is there. Thermally insulating vessel means neither heat is coming out nor the mass is coming out. This isothermal heat is coming out. This will be called as conducting wall. Whenever we have conducting vessel, if the vessel is conducting means thermally conducting, so heat can flow between the system and surrounding. So this delta is to NCV delta T, and we have work done. So from here we can calculate work done. So what is work done? If we talk about this Q, what is Q? Q is equal to delta U plus W. Okay, Q is delta plus W. So Q is 0. So delta U plus W. So what is W? Minus of delta U. Remember this. So W equals to minus of delta U in adiabatic process. So W is equals to minus of NCV delta T. W is equals to minus of this, or we can write in terms of this, P2 V2 minus P1 V1 divided by 1 minus gamma. Either this formula or sometime will be used this formula in terms of the NR, T2 minus T1 divided by 1 minus gamma. This will be adiabatic process. So let's see some of the graphs for this. So if we talk about the PV graph, if we talk about the isobaric process, this will be pressure, and this side volume we have. So this side PV curve, this is isobaric process. Isobaric process. Next we have this side isothermal. This side we have adiabatic, and this side here we have isochoric. This will be isochoric. So this will be isobaric when the pressure is constant. This side isothermal, and this will be adiabatic, and this will be isochoric. Adiabatic curve will always lie below the isothermal. Remember this. Adiabatic curve will always lie below the isothermal curve. So this will be this particular graph, that is straight graph, pressure versus volume. This will be isobaric. Next, this particular graph. So fourth one is what? Fourth one is isobaric. So this one is isobaric. Fourth one is isobaric. Next we have this third one, this particular graph. Below this will be isothermal, and again below this, when the temperature is also changing, this will be adiabatic. So second one will be adiabatic. So this will be adiabatic. This will be isobaric. Third one, this will be adiabatic, and this one is isothermal. This second will be isothermal, and last one that we have this graph, this particular graph where the volume is constant. So this graph will be isochoric, right? So process one will be isochoric. So remember this particular case. So this will be isobaric, isothermal, adiabatic, and isochoric. Two cylinders A and B of equal capacities means they are having equal or are connected to each other via a stopcock. A contains an ideal gas at standard temperature and pressure, and B is completely evacuated. The entire system of thermally insulated. The stopcock is suddenly opened. Thermally insulated. No need to solve this particular question. They already mentioned what? The entire system is thermally insulated. So whenever thermally insulated means there is no heat exchange from the surrounding and the system. Process is adiabatic. Process will be adiabatic. So if delta U and delta W represent the increase in internal energy and work done by the system respectively in a thermodynamic process, which of the following is true? So Q is equal to, if I write this, Q is equal to delta U plus W. So let's say write in terms of delta W as per given question. So here if you write adiabatic process, yes, adiabatic process, what is Q value? Q value is 0 in case of adiabatic process, yes. So from here I can write here delta U plus delta W is equal to 0. We are getting this delta U is equal to minus of delta W. Okay, right. Next we have delta U is equal to delta W in isothermal process. No, delta U isothermal process means delta U value is 0. So delta U value is 0 means from here we can say Q is equal to delta U plus W. Delta U value is 0 means Q is equal to W. We can't say from here. This one is correct. Delta equals to delta W in adiabatic process minus W, not plus W. This will be minus W. This is also wrong. Last one, again this isothermal process, this will also be wrong. Answer is option A. So let's solve this. This is what they're asking. For the given cycle, the work done during the isobaric process, we have to identify where the isobaric process. So this particular point where the pressure is constant, this side up to this point pressure is constant, that is the isobaric process. So this particular point we have to find this total area that is bounded by this, and as we calculate this total area, we'll get the work done. So what is total area? This we are getting rectangle. So this one is 3 and this one is 1. So what we are getting this 3 minus 1 multiply by this side here we have, sorry, this one is 0. We have to take this area, and this is 3 into 10 to the power 2. 3 into 10 to the power 2 minus 0. That's it. So we are getting this 3 into, so this will be getting in terms of this 600 joule. Answer will be 600 joule. They are asking for the isobaric process. So this total area that we have to focus here. This is the isobaric process. Okay, right. During an isothermal expansion, a confined ideal gas does minus 150 joule of work. So this against the surrounding. Confined means the gas is confined over here. So during isothermal expansion means temperature is constant. When the temperature is constant, we will be writing this Q is equal to delta U plus W. So delta U value is 0 because temperature is constant. So Q is equal to W. So Q is equal to W we will write. So how much W? That is minus 150 joule. So minus 150 joule. So 150 joule minus is there. So heat will be rejected or heat has been removed by the gas. If it is added to the gas, this will be plus 150. An ideal gas is compressed to half its initial volume by means of several processes. Which of the following process result in maximum work done on the gas? So when we talk about the work done on the gas, so here we can note down this. If we talk about the graph of this, so this is isobaric process, isothermal process, adiabatic process, isochoric process. This is expansion of the gases. This is for expansion of the gases, pressure versus volume. And if we have volume, pressure versus volume for compression of the gases. So this will be now start from higher volume, go to this isothermal, adiabatic, and this side isochoric. So in this case, you can note down work done in isobaric process will be more than work done in isothermal process, will be more than work done in adiabatic process, and last one, work done in isochoric process is 0. So we're not considering that. So this happens during expansion. Remember this result, because this area will be more for isobaric, then this area will be less for isothermal, then this area will be less for adiabatic, and the process is just reverse. So this will be isobaric, this will be isothermal, and this will be adiabatic, and this will be isochoric. So in this case, work done in isobaric will be less than work done in just reverse of this isothermal, and will be less than work done in adiabatic. So maximum work done in case of compression, as per the given, compressed to have an initial volume, it will be under which case? Adiabatic case. Clear? A monatomic gas at pressure P having volume V expand isothermally to volume 2V and then adiabatically to volume 16V. So initially state 1 of the gas we have, pressure is P, volume is V. State 1, it is going to state 2 of the gas. State 2 of the gas, pressure is, what is pressure now? Pressure we don't know. Let's say pressure is P2, and what is volume? Volume is 2V. So this process is isothermal, and we know in isothermal what happens. Isothermal process, P1 V1 is equals to P2 V2. So we can calculate directly from here, P into V is equals to P2 into 2V. So what is P2? We are getting this, V or V cancel, we are getting this, P2 is equals to P by 2. So this point we got the pressure, I am directly writing here, pressure is P by 2. Next, what is the state 3 of the gas we have? State 3 of the gas, adiabatically to volume 16V. So initially pressure is P by 2, now the pressure is, let's say, P3, and volume is, let's say, how much? 16V. So from this process is what? Adiabatic. And what is adiabatic process we have? Adiabatic process we have PV ki power gamma is equals to constant. PV ki power gamma equals to constant. So this side P by 2 into 2V to the power gamma is equals to this side P3 into 16V. So this will be 16V to the power gamma. P1 V1 equals to P2 V2. So solving this, what is gamma value? 5 by 3. So this, if we solve this particular case, we'll be writing this. So what is P3 that we'll be writing here? P3 is given by P by 2 into this side 2V divided by 16V to the power 5 by 3. Yes or no? So this volume or volume cancel. This is 2 1 ja, this is 2 8 ja. So this we are getting finally, that is P3. Final pressure is given by this P by 2 into this side 1 by 8 to the power 5 by 3. 1 by 8 to the power 5 by 3. 8 to the power 1 by 3, 2 to the power 5, that is, we'll be writing this. So 32. So this will be P by 64 we are getting. P by 64. Okay. So this simple formula we are using, PV power gamma equals constant for adiabatic process. Next one, this particular question, they're asking what? 1 mole of an ideal diatomic gas undergoes a transition from A to B along the path AB as shown in the figure. So this point at A, I will tell you what is the pressure they have mentioned, 5 into 10 to the power 3 Pascal. So this is pressure P1. And what is volume? Corresponding volume here, that is 4 meter cube. At point B, what is the pressure they have mentioned? 2 into 10 to the power 3 Pascal. That is pressure. And what is volume at the same position? That is, volume is 6 meter cube. What they are asking? Change in internal energy. We got the one formula. What is delta U? What is delta U in terms of this? So this delta U is P2 V2 minus P1 V1 divided by gamma minus 1. That's it. We can use this direct formula directly over here. It is going from A to B. A to B. So what is P2 V2? So this side delta U will be given by P2 into V2. So what is P2 here we have? 2 into 10 to the power 3 into volume 6 minus V2 P1 V1. So 5 into 10 to the power 3 into volume 4 divided by gamma. What is gamma for ideal diatomic gas? Gamma is 5 by 3. Okay. So this, gamma is, this is for monatomic gas. Gamma for ideal diatomic gas, gamma is 7 by 5. So we are getting from this 7 by 5 minus 1. Right? So this will be 7 by 5 minus 1. So solving this particular case, we are getting this. How much will be getting? So 6 into 2, that is 12 into 10 to the power 3 minus 20. So this 6 into 2, 12 minus 20, 20 into 10 to the power 3 divided by, so minus 20 into 10 to the power 3 divided by 2 by 5. So this will go up and we'll be getting, so 7 by 5 minus 1. 6 and 12 minus 20. So this will be minus 8. Minus 8 into 10 to the power. So this 8 10 to the power 3. So 8, this will 8 into 5 by 2. We are getting minus 20 into 10 to the power 3. So minus 20 kilojoule. Answer is option D. Minus 20 kilojoule. Clear? So this we are getting, like, we can directly we can solve from the graph as well, directly this point A and this point B. We know the initial pressure, initial volume, and we know the final pressure, final volume. From that we can calculate directly change in internal energy. Next we have, that is polytropic process and cyclic process. What is cyclic process? If we talk about the cyclic process, I went from A to B and again come back to B to A. So this point is A, this point is B, A to B and come back to B to A. So this process, if I tell you, you can see this process is looking like clockwise. So this is clockwise process. So in clockwise process and anti-clockwise process, one difference is there. So whenever it is starting from point A, going to point B, again coming back to point A, initial state and final state is same. So what is delta U? Delta U value will be 0. And what is Q? Q is equal to delta U plus W. So what is Q? Q will be writing here W. And what is W? Delta U is 0. So Q is equal to W. What is W? W will be area of this graph, area of this loop. So area of the loop will give us work done. Okay, area of the loop will give us work done. So this area of the loop will give us work done, and this work done will also be equal to heat that what we are supplying, total heat we are supplying. If this loop is clockwise, remember this. If this one is clockwise, we have to take work done positive. Okay, we have to take work done positive. In the second case, suppose if the loop is anti-clockwise, everything will remain same. So starting from point A and this point B, and let's say we are going like this, we are going A to B like this, then we are coming B to A like this. So in this case, the loop is anti-clockwise. ACW, that is loop is anti-clockwise. Again, area will give us work done. Area will give us work done, but here work done will be negative. Here the work done will be positive because clockwise work done we have to take it as positive. Anti-clockwise work done, this will be work done will be negative. Again delta U will be 0. Delta U value will be 0 because initial state and final state is same. Delta U is 0. So what is Q? Q is equals to W. If W is positive means net gas is doing, W is positive means gas is doing the work. If the W is negative means gas is not doing the work, means we are doing the work on the gas. So here Q is negative means the heat is released by the gas. So heat is released by the gas in this case, and in this case the heat will be absorbed by the gas. These two things that we should keep in mind for this cyclic process. And what is polytropic process? The polytropic process in general, any slow process in which the system is always in equilibrium with all the particles, so that process will be defined as polytropic process. So polytropic process will be writing this PV ki power x is equals to constant. Any slow process in which all the pressure and volume, pressure and temperature throughout the entire volume of the gas remains constant, that slow process we define the polytropic process, and that is we define the PV ki power x equals to constant. So PV ki power x equals to constant, from here we can write x is what? X is polytropic constant. So x will be polytropic constant. When the polytropic constant in terms of this, if you write, so this molar heat capacity we can write here Cv plus R divided by 1 minus x. For this particular process, molar heat capacity is given by this. And for this process, W is also given like this, that is P2 V2 minus P1 V1 divided by 1 minus x. Again, x is the polytropic constant. Second, if you write this work done, we can write here NR T2 minus T1 divided by 1 minus x. This also work done in polytropic process. So these are the formulas we have for the polytropic process. So let's discuss this particular question. What is it asking? If the gas is taken, they have given the cyclic process, the gas is taken from A to B, B to C, then C to A. What are they asking? Total work done by the gas. The total work done by the gas will give given by area of the loop. So this area of the loop will give us total work done by the gas. What is area? So this one is 2 and this one is 7. So base is how much? 5. And this side here we have again 2 and this side here we have 6. So this base is 5, that is multiply by this is 6 minus 2. So 6 minus 2, how much we are getting this? 5 into 4 divided by 2. So 5 into 4 divided by 2. And in terms of this, so we got the volume 5 into 4 divided by 2, that is 10. And this is in terms of 10 ki power minus 3, and this is in terms of the kilopascal we have. So this will be approximately this, whatever we are getting. So 10 is matching over here, so this will be 10,000 that we will be getting. So this is in terms of the 10 ki power minus 3, and this will in terms of the 7 10 ki power 5 Pascal. So answer will be here 1000 joule. What is the net work done by the gas? The thermodynamic system is taken through a cycle A, B, C, D, A, work done by the gas along path BC. So this question came in last year. So along this particular path B and C, when we are going from B to C, what is the work done? No work is being done here. Why? Because you can check the volume is constant. So in this case, what is volume? So when the volume is constant, B to C, which process here we have? B to C is which process? Isochoric process, right? Isochoric process. So no work done is, so in this case B to C, no work done will be there because isochoric process, the answer will be 0. This also came in some previous year NEET question. So a thermodynamic system undergoes cyclic process A, B, C, D as shown in the figure. The work done by the system, you can check it. So if we talk about this, if we talk about this particular loop, you can check it. This loop is clockwise, anti-clockwise. This loop is clockwise. And if I talk about this particular loop, this loop is anti-clockwise. So this is clockwise work done, we have to take it as this will be positive. And this is anti-clockwise work done, we have to take it as this one as negative. So this will be clockwise and this will be anti-clockwise. So positive equal positive, because this triangle and this triangle will be having equal and opposite. So this one is positive, this one is negative. So what is total work done? It will be 0. Clear? So even the question is looking like different, little bit different, but we just have to focus on the area. This area and this area, both will be same. And first one is positive, second one is negative. 1 mole of an ideal monatomic gas undergoes a process described by the equation PV की power 3 equals to constant. The heat capacity of the gas during this process will be given by. So if we talk about this, PV की power 3 is equals to constant. Compare this with PV की power x is equals to constant. What I told, heat capacity. What is heat capacity for this process we have? For this process we have, what is that? CV plus R divided by 1 minus x. So this is the heat capacity we have, CV plus R divided by 1 minus x. Putting this value, compare this, we have this, what is x value from this? If you compare this, x value is given by 3. X is given by 3. So putting the value here, so C is equals to CV plus R divided by 1 minus 3. And what is this value? CV value. Which gas it is here we have? Ideal monatomic gas undergoes a equation PV की power 3 equals to constant. So ideal monatomic gas. So ideal monatomic gas, what is CV value? Yes, we have to remember this. CV value is 3R by 2. What is CP value? 5R by 2. So this side C is equals to 3R by 2 plus R by minus 2. So we are getting this C value, R by 2 common. So this we are getting here. 3 by 2 minus R by 2. What we are getting here? This value we are getting as, okay. So this particular question, again, this is Carnot engine. Last year, some of the question they asked from this. So let's solve little bit about this. Let's discuss little bit about it, Carnot engine. So if we see how an ideal gas heat engine operates in Carnot cycle. So here we have, this side will be having source temperature. This side will be having source. And this side will be having sink. Between 227 and 127 degrees Celsius. So this side 227 degrees Celsius. And this side here we have 127 degrees Celsius. It absorbs 6 into 10 to power 4 calorie of heat at higher temperature. Always remember this. So there will be, setup will be like this, such that here we will be having two temperature bodies. One is higher temperature body and second is lower temperature body. The higher temperature body will be having temperature of higher temperature body will be called as source, and other we call it as, other will be called as 120 degrees Celsius, that will be called as sink. So this is 120 degrees Celsius, lower temperature will be called as sink. So here and between the gases will be there. The gases will be taking heat from here, and that heat is Q1. The gases will be rejecting heat to here, and that heat is Q2. And the gases will be doing some amount of work. So if we see the energy flow, how the energy flow happens. So Q1 is the supply energy, and out of this Q1, this will be Q2 plus W. So this Q1 is the energy that is being supplied by this higher temperature body, and this body is doing this gas. This gas is absorbing some amount of heat and doing some useful work W, and some part of this gas is removed to this thing. Some part of this heat is removed to this particular sink. That is how much? 127 degrees Celsius. So it is taking Q1, Q2 plus W. And what is efficiency we define? Efficiency always define what is the work output we want from here, that is W. And what is the input we are giving here? Q1. So if we solve this, so what is eta? W by Q1. And what is Q1? What is W? We can write here Q1 minus Q2 divided by again Q1. So what is eta we have? 1 minus Q2 by Q1. This is what we are getting efficiency of the heat engine, Carnot engine. 1 minus Q2 by Q1. So we have the temperature. Again, Q is directly proportional to temperature. So if we see, what is eta we are getting? 1 minus Q2 by Q1. 1 minus Q2 by Q1. So this side, so eta is given as 1 minus T2 by T1 also, because Q is proportional to temperature. So Q2 by Q1 equals to T2 by T1. So that's it. So what they're asking, we can calculate this. Eta value is 1 minus T2 by T1. We have to write in terms of the Kelvin. T2 is 127. So T2 is equals to 127 plus 273. How much we got? This we got 400 Kelvin. And this is plus 100 we have to add. So this will be, temperature for this will be 500 Kelvin. This is T1, that is 500 Kelvin. So putting this value, so 1 minus 400 divided by 500. 400 divided by 500 is equals to efficiency. And efficiency, one more formula that we have now, that is W by Q1. So this W by Q1, that's it. So from here we can write 100 divided by 500 is equals to W by Q1. So what is W from here? So W is equals to Q1 multiplied by 100 divided by 500. So what is Q1 value? How much heat we are supplying? How much heat we are supplying? 6 into 10 to the power 4. So this will be 6 into 10 to the power 4 divided by 5. How much we got? That is 1.2 into 10 to the power 4. Answer is option D. So 1.2 into 10 to the power 4. Right? So that's all for today. That we covered some of the questions. We covered the graphs, we covered the different processes, we covered the kinetic theory of the gases. Please go and revise. So in physics, mostly you have to revise like concept from the different processes and their graphs, corresponding graphs they will be asking. Some polytropic process, the extra process, cyclic process, the extra process over here. So please go and revise those concepts. Tomorrow will be coming this topic, oscillation in waves. Yes, little bit bigger chapter if you combine both. They are having separate chapters, oscillation and waves, but we'll try to combine because we have less number of times. We have less time. So for that, we'll be discussing tomorrow what is equation of the SHM, waves and their basic terms, time period of oscillating bodies, standing waves, that is open organ pipe, closed organ pipe, normal mode of oscillation like standing waves will be discussing tomorrow in tomorrow's class. But till now, prepare well, do your best and keep practicing the questions. Thank you.